quantitative analysis, we now quantify the behavior of a MOS differential pair as a function of the input differential voltage. We begin with the last signal analysis to arrive at an expression for the plot shown in figure. Here you can see the figure differential pair. For the differential pair in figure, we have V out 1 equal to VDD minus RD1 ID1 and V out 2 is equals to VDD minus RD2 ID2, that is V out 1 minus V out 2 is equals to RD2 ID2 minus RD1 ID1 is equals to ID2 minus RD into ID2 minus ID1 if RD1 is equals to RD2 is equals to RD. Thus we simply calculate ID1 and ID2 in terms of V in and V in 1 and V in 2, assuming the circuit is symmetric. M1 and M2 are saturated and lambda equals 0, since the voltage at point P is equal to V in 1 minus VGS1 and V in 2 minus VGS2. V in 1 minus V in 2 equal to VGS1 minus VGS2. For a square law device, we have VGS minus VTH whole square equal to ID by 1 by 2 nu and C naught x W by L, and therefore VGS is equals to root over 2ID by nu and C naught x W by L plus VTH. It follows from equation that V in 1 minus V in 2 is equals to root over 2 ID1 by nu and C naught x W by L minus root over 2 ID2 by nu and C naught x W by L. Our objective is to calculate the differential output current ID1 minus ID2, squaring the two sides of equation and recognizing that ID1 plus ID2 is equals to ISS. We obtain V in 1 minus V in 2 whole square is equals to 2 by nu and C naught x W by L into ISS minus 2 root ID1 into ID2, that is 1 by 2 nu and C naught x W by L V in 1 minus V in 2 whole square minus ISS is equals to minus 2 root over ID1 into ID2. Squaring the two sides again and noting that 4 ID1 ID2 is equals to ID1 plus ID2 whole square is minus ID1 minus ID2 whole square is equals to ISS square minus ID1 minus ID2 whole square. We arrive at ID1 minus ID2 whole square is equals to 1 by minus 1 by 2 nu and C naught x W by L whole square V in 1 minus V in 2 to the power 4 plus ISS nu and C naught x W by L V in 1 minus V in 2 whole square. Thus ID1 minus ID2 is equals to 1 by 2 nu n C naught x W by L V in 1 minus V in 2 into root over 4 ISS by nu n C naught x W by L minus V in 1 minus V in 2 whole square. As expected, ID1 minus ID2 is an odd function of V in 1 minus V in 2 falling to 0 for V in 1 is equals to V in 2, as mod V in 1 minus V in 2 increases from 0 mod ID1 minus ID2 also increases because the factor preceding the square root arises more rapidly than the argument in the square root drops. Before examining equation further, it is instructed to calculate the slope of the characteristic, that is the equivalent GM of M1 and M2, denoting ID1 minus ID2 and V in 1 minus V in 2 by mod ID and mod V in respectively. The reader can show that dou lambda ID by dou delta ID by dou delta V in is equals to 1 by 2 nu n C naught x W by L into 4 ISS by nu n C naught x W by L minus 2 delta V in square by root over 4 ISS by nu n C naught x W by L minus delta V in square. For V in is equals to 0, GM equal to root over nu n C naught x W by L ISS. Moreover, since V out 1 minus V out 2 is equals to RD, the delta I is equals to RD GM delta V in, we can write the small signal differential voltage gain of the circuit in the equilibrium condition as the delta mod AV is equals to root over nu n C naught x W by L ISS RD. It is interesting to note that even though ID1 and ID2 are even functions of their respective gate source voltages, ID1 and ID2 is an odd function of V in 1 and minus V in 2. This effect is studied in chapter. Equation also suggests that GM falls to 0 for delta V in is equals to root over 2 ISS by nu n C naught x W by L. Also, we see below this value of delta V in plays an important role in the operation of the circuit. Let us now examine the equation more closely. It appears that the argument in the square root drops to 0 for delta V is equals to root over 4 ISS by nu n C naught x W by L, implying that delta ID crosses 0 at two different values of delta V. This was not predicted in our qualitative analysis in figure. This conclusion, however, is incorrect. To understand why, recall that equation was derived with the assumption that both M1 and M2 are on. In reality, as delta V in as its limit, one transistor carries the entire ISS turning off the other. Denoting this value by delta V in 1, we have ID1 is equals to ISS and delta V in 1 is equals to VGS1 minus VTH, because M2 is nearly off. It follows that the delta V in 1 is equals to root over 2 ISS by nu n C naught x W by L. For delta V in greater than delta V1, M2 is off and equation does not hold. As mentioned above, GM falls to 0 for delta V in is equals to delta V in 1. Figure plots the behavior. Here you can see the figure, variation of drain currents and overall transconductance of a differential pair versus input voltage. The value of delta V in given by equation is in essence represents the maximum differential input that the circuit can handle. It is possible to relate delta V in to the overdrive voltage. We neglect threshold conditions here. Here you can see the figure of M1 and M2 in equilibrium for a zero differential input. ID1 is equals to ID2 is equal to ISS by 2, and hence VGS minus VTH 1 2 is equals to root over ISS by nu n C naught x W by L. Thus the equilibrium overdrive is equal to delta V in 1 by root 2. The point is that increasing delta V in 1 to make the circuit more linear inevitably increases the overdrive voltage of M1 and M2 for a given ISS. This is accomplished by only reducing W by L and hence the transconductance of the transistors. Now we study the small signal behavior of differential pairs as depicted in figure. We apply small signals V in 1 and V in 2 and assume M1 and M2 are saturated. That is, for what is the differential voltage gain? V out by V in 1 minus V in 2. Recall from equation that this quantity equals root over nu n C naught x ISS W by L RD, since in the vicinity of equilibrium, each transistor carries approximately ISS by 2. This expression reduces to GMRD, where GM denotes the transconductance of M1 and M2 to arrive at the same result by small signal analysis. To arrive at the same result by small signal analysis, we employ two different methods, each providing insight into the circuit's operation. We assume RD1 is equal to RD2 is equals to RD. Here you can see the figure differential pair with small signal inputs. Figure A, differential pair sensing one input signal B, circuit of A viewed as a CS stage D generated by M2C, equivalent circuit of B. Method 1. The circuit of figure is driven by two independent signals, thus the output can be computed by superposition. Let us set V in 2 to 0 and find the effect of V in 1 at X and Y. Figure A. To obtain Vx, we note that M1 forms a common source stage with a degeneration resistance equal to the impedance seen looking into the source of M2. Figure B. Neglecting channel length. Here you can see the figure replacing M1 by Thevenin equivalent. Modulation modulation and body effect. We have Rs is equals to 1 by Gm2 figure C, and Vx by Vin is equals to minus Rd by 1 by Gm1 plus 1 by Gm2. To calculate Vy, we note that M1 drives M2 as a source follower and replace V in 1 and M1 by a Thevenin equivalent figure. The Thevenin voltage Vt is equals to V in 1 and the resistance Rt is equals to 1 by Gm1. Here M2 operates as a common gate stage, exhibiting a gain equal to Vy by Vin is equals to Rd by 1 by Gm2 plus 1 by Gm1. It follows from equation that overall voltage gain for Vin1 is Vx minus Vy due to Vin1 is equals to 2Rd is equals to Rd by 1 by Gm1 plus 1 by Gm2 into Vin1, which for Gm1 is equal to Gm2 is equal to Gm reduces to Vx minus Vy due to Vin1 is equals to minus Gm Rd V1. By virtue of symmetry, the effect of Vin2 at x and y is identical to that of Vin1 except for a change in the polarities. Vx minus Vy due to Vin2 is equals to Gm Rd Vin2. Adding the two sides of equation to perform superposition, we have Vx minus Vy taught by Vn minus Vn1 minus Vn2 is equals to minus Gm Rd. Comparison of equations indicates that magnitude of differential gain is equal to GMRD regardless of how the inputs are applied. In figures, the input is applied only to one side, whereas in figure the input is the differential between two sources. It is also important to recognize that if the output is single-ended, that is, it is sensed between x and y and the ground, the gain is halved. How does the gain of a differential pair compare with that of a common source stage? For a given total bias current, the value of Gm in equation is 1 by root 2 times that of a single transistor biased at ISS with the same dimensions. Thus, the total gain is proportionally less. Equivalently, for given device dimensions and load impedance, a differential pair achieves same gain as a CS stage at the cost of twice the bias current. Method 2. If a fully symmetric differential pair senses differential inputs, that is, two inputs change by equal and opposite amounts from the equilibrium condition, then the concept of half circuit can be applied. We first prove a lemma. Consider the symmetric circuit shown in figure A, where D1 and D2 represent. Here you can see the figure. Illustration of Y node P is a virtual ground. Any three-terminal active device, suppose Vin1 changes from V0 to V0 plus delta Vin and Vin2 from V0 to V0 minus delta Vin. Figure B. Then if the circuit remains linear, VB does not change. Assume delta equal to 0. Assume delta is equals to 0. Proof. Let us assume that V1 and V2 have equilibrium value of VA and change by delta V1 and delta V2 respectively. Figure C. The output currents therefore change by Gm delta V1 and Gm delta V2. Since I1 and I2 is equals to IT, we have Gm delta V1 plus Gm delta V2 is equals to 0. That is delta V1 is equals to minus delta V2. We also know V in 1 minus V1 is equals to V into minus V2, and hence V0 is plus delta V in minus VA plus delta V1 is equals to V0 minus delta V in minus VA plus delta V2. Subsequently, 2 delta V in is equals to delta V1 minus delta V2 is equals to delta V1. In other words, if V in 1 is equals to V into change by subsequently change we also know V in 1 minus V1 is equals to V into minus V2, and hence V0 plus delta V in minus VA plus delta V1 is equals to V0 minus delta V in minus VA plus delta V2. Subsequently, 2 delta V in is equals to delta V1 minus delta V2 is equals to 2 delta V1. In other words, if V in 1 and V in 2 change by plus V plus delta delta V in and minus delta V in respectively, then V1 and V2 change by the same values, that is differential change in the input simply absorbed by V in 1 and V in 2. In fact, since Vp minus V in 1 minus V1, and since V1 exhibits the same change as V in 1, Vp does not change. The proof of the foregoing lemma can also be invoked from symmetry as long as the operation remains linear, so that the difference between the bias currents of D1 and D2 is negligible. The circuit is symmetric, thus Vp cannot favor the change at one input and ignore the other. From yet another point of view, the effect of D1 and D2 at node P can be represented by Thevenin equivalence figure. If Vt1 and Vt2 change by equal and opposite amount, and Rt1 and Rt2 are equal, then Vp remains constant. We emphasize that this is valid if the changes are small, such that we can assume Rt1 is equals to Rt2. Our 4. The above lemma greatly simplifies the small signal analysis of differential amplifiers as shown in figure. Since Vp experiences no change, node P can be considered AC ground, and the circuit can be decomposed into two separate halves. Hence, term half circuit concept, we can write Vx by V in 1 is equals to minus Gm Rd, and Vy by minus V in 1 is equals to minus Gm Rd, where minus Gm Rd, where V in 1 and minus V in 1 denote the voltage change on each side. Thus Vx minus Vy by 2V in 1 is equals to minus GMRD. It is also possible to derive an expression for large signal behavior of Vp and prove that for small V in 1 minus V in 2 Vp Vp remains constant. We defer this calculation to chapter. Here you can see in this figure replacing each half of a differential pair by a Thevenin equivalent. Here you can see in this figure application of half circuit concept. The half circuit concept provides a powerful technique for analyzing symmetric differential pairs with fully differential inputs. But what happens if the two inputs are not fully? Here you can see in this figure conversion of arbitrary input to differential and common mode components. A differential figure A. As depicted in figures B and C, two inputs V1 and V2 can be viewed as V1 is equals to V1 minus V2 by 2 plus V1 plus V2 by 2. V2 is equals to V2 minus V1 by 2 plus V1 plus V2 by 2. Since the second term is common to both inputs, we obtain the equivalent circuit in figure D, recognizing that the circuit senses a combination of a differential input and a common mode variation. Therefore, as illustrated in figure, the effect of each type of input can be computed by superposition with the half circuit concept applied to the differential mode operation. Here you can see in this figure superposition for differential and common mode signals. Solution Thank you.